are electromagnetic waves that we have seen. Now coming to this main formula of magnetism that I told you we'll have to discuss here. So this is the electric field. See, this will tell you the quantity that is present, whether it's electric field or magnetic field. Like this tells us that this is the electric field existing. And this also tells us where the electric field is existing along whichever axis. Now, it's a wave. Wave will have a higher value, a lower value, a higher value, and descending to a lower value like this. So this E naught, this is basically the peak value, means the maximum displacement that is possible. Like this one, this is the peak value, the maximum displacement. So this E naught is actually the peak value of electric field. Okay. Now for sine, this is just your normal function, sine or cosine, anything can be written. Sine can be written, cos can also be written. Okay, I told you this in the last classes. Now K. K is basically angular wave number. Angular wave number. Angular wave number means, see class, whenever you have any wave propagating, let's say there is one wave. Let's say this is how the wave is propagating. So before the wave starts repeating itself at this point, from this point, this is one wavelength. It could be between two consecutive crests also, two consecutive troughs also, and between one complete nodal end also. So that is known as the wavelength. So wavelength, there's a constant which is known as the angular wave number that is equal to 2 pi by lambda, where your lambda is actually the wavelength present. This is the wavelength present. Okay. Now see, coming to this X symbol actually tells us about the direction. Where is the wave propagating? Okay, direction of propagation. See, this is telling the direction of electric field. This will tell the direction of propagation. Direction of propagation. Okay, this is the direction of propagation. Like if it is written X means X axis, Z will also be written, Y will also be written, anything can be written. But when I say Y, it doesn't mean here also Y will be there. It will be something else because all the three are perpendicular to each other. Now this plus minus sign, this is whatever will appear, actually it won't be. That means if you have a positive sign, this is just for direction of propagation is fine. But which axis? If I say X could be negative X axis also, positive X axis also. So which one? So when I say positive, this is the negative X axis actually, not a X axis, any negative axis. And if minus sign is used, actually it's the positive axis. This is what these plus minus signs will tell. Mostly you have, not mostly, you can have anything actually. Okay, what is omega? Omega is the angular frequency. Angular frequency, which you know omega is equal to 2 pi into the linear frequency. Linear frequency is 1 by time. Omega is equal to 2 pi by t. All these equations will be used again. And t is for the time. So these equations are very important. One recent board's question came. I mean, once a question recently has come. Secondly, if I take the same thing for a magnetic, now I'll not explain you that again. You'll be able to do. Let's say your electric field is along the y-axis. This is along the x-axis direction. We are left with z-axis. So magnetic field will be across the z-axis with V naught sine kx plus minus omega t, like this. The same thing, peak value of magnetic field, this is how it will be different. Difference will be that this is the magnetic. This is the magnetic. And B naught will be the peak value of magnetic field, sine kx plus minus omega t, everything will be the same, so that I am not. Now, next is the definition of EM wave. An electromagnetic wave is a wave radiated by an accelerated charged particle. Okay, accelerated charge. You will see when we discuss the electromagnetic spectrum, that time you will see various particles are accelerated, and that's how a wave is created. Now, why? Because acceleration of the charged particle will have electric field component already, and movement of charge means current can lead to magnetic field as well. So at the micro level, these are the same things that you've already studied. So you don't need to go into the details. You already know the basics. Just combine electric field and magnetic field in your mind, and which propagates through space as coupled electric and magnetic fields. Oscillating perpendicular to each other means electric and magnetic are perpendicular to each other, as well as perpendicular to the direction of propagation. Now the whole gist of what we did in the last class, the figure that I had drawn, the graph part, this part that we saw, the electric field is there, magnetic field is there, direction of propagation. Is it clear? All right. Copy down this. I think this graphical part you all have written, or was it supposed to be written?
No, ma'am, done.
Written. Okay. So from here, right, then we'll see what? We'll see the properties first. Spectrum, I'll tell you later on. I'll have to show you a chart. From here, I won't be discussing. So that I'll discuss later. First, write it. Done? Us also? Ali done? Halima?
Yes, ma'am.
Okay. Take your mind, discuss later. Let me come to the properties first, because it's in continuation with what we have just studied. First property is very simple. Electric field, magnetic field, direction of propagation. All of them will be perpendicular to each other. One more thing, Ali, your exam was today or is it tomorrow?
It was today.
So Ali, why did you inform them for a class today?
Ma'am, I informed them for yesterday.
Okay, all right. Yesterday, your class was supposed to be yesterday. They told me that you want a class on Thursday and your class will be arranged after this class ends. So that's why you've informed them that did you inform them that your exam was on 18th?
Ma'am.
And how did it go, by the way?
It was easy.
It was easy.
Yes, ma'am.
So this was your half yearly.
No, ma'am, PT2.
Okay, PP2 half yearlies are done.
Yes, ma'am.
Oh. Okay, electric field, magnetic field, and direction of propagation. They are perpendicular to each other. Second is the magnetic force is equal to the electric force. So QVB is equal to Q into E. That charge will be cancelled. So speed is actually electric field by the magnetic field. Now, if we take the peak values, or in fact, not the peak values, if I take electric field for air, magnetic field for air, so I'll get the speed also for air. So that is basically the speed of light, which is 3 into 10 to the power 8 meter per second. Those who do not remember this value, remember it from now onwards, because this value will be used in this chapter, in ray optics, in wave optics. At least in these three chapters, this value will be used. And it's a very easy value which you should be knowing. Okay, it's the speed of light in air, in vacuum. So usually the ratio that you have to take for the speed is electric field by the magnetic field. But when we talk about particularly for air, we'll use the speed of light. Now, how to calculate the speed of EM wave? There's one formula that you have. C is equal to 1 by under root mu naught into epsilon naught. Mu naught is your permeability from magnetism, and epsilon naught is basically the permittivity from electrostatics. So exactly the same thing. This formula you don't need to derive, but one thing, if you put in the values here, if I put, let's say this is mu naught is 4 pi into 10 to the power minus 7. This is mu naught. Then we have epsilon naught into 8.85 into 10 to the power minus 12. When you will put, you will get this value as 3 into 10 to the power 8 meter per second. No need to calculate and check. This is the value that you will get, which is the speed of light in air. But everything is about air. What if the medium is changed? Electromagnetic waves are not just adhered to one particular medium, that is your vacuum. So what if the medium is changed? So one of the formula that we discussed was that the relative permittivity is equal to the permittivity in any medium by the permittivity in air. That's what we've already studied, that relative permittivity is permittivity in any medium by the permittivity in air. Similarly, the relative permeability, that is also permeability in any medium by permeability in air. So from here, see, epsilon and mu will not be given to you. These will not won't be given to you. You will be given the relative values. So you'll just have to multiply it with the original. See how? If I say, let's say now the speed is some v, not this c, because c is exclusively for your speed of light. So this is v. V is equal to 1 by under root epsilon into mu, because the material medium has changed. Now write this in terms of the relative permittivities. Just in case if the question gives you the values of these absolute ones in the medium, then you use this formula. But that's rarely given. Why would somebody give you these two values and put it in this formula? Means when one or two more steps can be given. And usually, calculation of the relative permittivity is done experimentally. So usually we have the relative permittivities and permeabilities value. Are you getting it? This will least be used. This will be least used. But anyways, if you have something, you'll have to follow it. And if it comes, then you use this. So this is C. Epsilon can be written as epsilon naught, epsilon r. Mu can be written as mu naught into mu r. Now speed will be 1 by. See, if I just rearrange the terms like this, epsilon naught, mu naught, epsilon r, mu r. See class, basically 1 into this whole term. If I take, what will be this?
C.
Yes, speed of light in the air, c. So we have a relation v is equal to c by under root epsilon r mu r. Got it? So this is one relation for the speed in any medium where the relative permittivities are mentioned. Otherwise, don't remember it like a derivation, just like remember them like steps, proper steps, so that whichever question comes, you're able to answer. Regarding the fifth and the sixth, okay, this I'll tell later. First, write down these first four properties, then the rest four I'll tell you. Please write it.
Done, ma'am.
Okay, see, for the fifth and the sixth point, these we'll do in the ray optics chapter. Basically, refractive index is a quantity that tells us about the optical density of material. Optical density of a material. So, the refractive index that is given is actually the ratio of the speeds. Let's say speed in one medium by speed in the second medium, or wavelength in one medium or wavelength in second medium. So since this is depending, refractive index is depending on the speed, and for the speed we have already seen the theory. That's why the refractive index also varies with the speed. Now, how does it vary? What is the refractive index? We will do it in the next chapter. Other is that all the optical phenomena means related to all these ray optics phenomena, reflection of light, refraction of light, absorption of light, and all transmission of light and all these things. So they are due to the electric fields component. Electric field means the component of from the electromagnetic field, the component of electric field that will be responsible for this ray optics part. Magnetic field won't have any contribution in this. Next is energy density. This is one of the most important topics. Energy density basically means energy per unit volume. Okay. Now, when we say energy per unit volume for electrical energy, the formula is electrical energy is actually half epsilon naught E square. While the magnetic energy, this is electrical energy, so I'll write UE. While the magnetic energy is half B square by mu naught. Okay, so half epsilon naught into E square, and the magnetic one is half B square by mu naught. These are the energies. This one, if you remember, we derived also, and I told you that electric field, electrical energy is directly proportional to electric field. Not Jovita. Safrina, you have done it recently, remember? In one of the backup classes, we did it. So that's how, So that's how you have to relate it. Now see, when we talk about the energies, actually this is the RMS value. Because electric field and magnetic field are variable in this chapter. That's what we started the chapter with, time varying electric field, time varying magnetic field. So electric field and magnetic field are variable with time. So when I say total energy density, these are the RMS values, means total energy will be electrical is half epsilon naught E square plus half B square by mu naught. Now this is also the RMS value. This is also the RMS value actually. So what if the peak value is given to you in the question? So same formula will be used the way we have studied already in the alternating current chapter. Okay, E naught by root 2, B naught by root. So ERMS square will be E naught square by 2, BRMS square will be B naught square by 2. So total energy density will be, we'll put this value as ERMS square. ERMS square will be E naught square by 2 into epsilon naught. While this part will be half, see, BRMS square will be B naught square by 2 into 1 by mu naught. Why 1 by? Because this is in the denominator. Here it's getting multiplied. If RMS values are given, you will say 1 by 4 epsilon naught E naught square plus 1 by 4 B naught square by mu naught. Am I clear? These are the peak values, these are the RMS values. Basically, you just have to add the energies. These are all energy densities itself included within them. Clear? Write these, then we'll discuss momentum and intensity. Right. Okay, talking about the momentum class, momentum of electromagnetic wave. So there is one formula of momentum, that is energy per unit, per speed of light. So this formula is hardly used, but I'll still mention it to you so that if it is asked in an exam, you can directly use it. What is important that I'll tell you? This is the momentum. By the way, what's the formula of momentum from class 11th?
M into V.
Yes, m into v, correct. This is energy, this is the speed of light. Now, is momentum scalar or vector? Scalar or vector? Because that changes everything if it's scalar or if it's vector. Class, look at the formula, mass into velocity. When velocity is, it's not mass into speed. Kinetic energy is half mv square, which is half into mass into speed square, not velocity square. If velocity is included, it will be a vector. Okay. Velocity when you have n multiplied to a vector, resultant is a vector. Anyways, why did I say this was? Let's say an EM wave has struck the surface. This is an absorbing surface. So the momentum, that is, let's say, some p. Now, if there's a reflecting surface, it will reflect the ray of this EM wave back, this wave back. So see, you will have to assume some sign convention here. Let's say we take up as positive and down as negative. Anything you can take. Up as positive. So this is down, this will be negative, this will be positive. Now here, when you calculate the change in momentum, it will be final minus initial. What is the final momentum? P minus initial momentum minus P. That is in fact P plus P, that is 2P. This is a question that has been asked a lot in the exam. Not a lot, once actually, one or twice. That what happens to the momentum in the case of EM waves in your reasoning questions. So many students write, means when this whole part is given, no, that a ray of light is coming and it is getting reflected back, what's the resultant momentum? Many students in zero. It's coming, it is getting opposite direction, it gets cancelled. No, when you apply proper vectors with sign convention, your answer changes. Actually, it doubles. So that's the real answer, it doubles. Okay. Even if you change the sign convention, it will be minus 2p. That shows the direction. If I'm getting positive, it means the resultant is is upwards. If I'll change the direction, I'll get this as negative. It will still be upwards. Your answer will be right. But remember, the momentum will be double of it. It's like the concept of the relative velocity. Okay, relative velocities and all, which you've done in 11th class. Now, what is intensity? Last property of an EM wave is, this is basically the energy per unit area per unit time. Just, can anyone tell me what is energy per unit time? Energy by time.
Some work.
Work done. Work done is energy only.
Some power.
Power. Very good, Alima. Power. This part, this is equal to power. Power is work done by time or energy by time. So you can say your intensity is equal to power divided by the area. This is a very important part. Questions have come often from this intensity part, not from this chapter, but from your waves chapter. This intensity formula can be used anywhere. This I'll tell you, because in other chapters it has been used. I remember the questions are there from intensity. Okay, so SI unit of intensity will be what per meter square? Okay, and use this formula of intensity as power by area. This is a common formula. Now we will do two numericals based on this. Two proper numericals that have recently come in the exams. Property. Otherwise, it's a very theoretical chapter. Also, most of the portions from spectrum, they are theory part. They are a part of the theory. Okay. So write it down, class. Am I clear till here? All the properties with the EM waves construction. Ali? Ali, you there? Okay. All right, then please write it.
Ma'am, can you scroll? Okay.
Done?
Yes, ma'am.
Okay. See, this question says a plane EM wave of frequency 25 megahertz travels in space. In free space along the x-axis means direction of propagation. Direction of propagation is along the x-axis. Okay, at a particular point in space and time, electric field is given. See, how is the electric field given? It is given as 6.3 J cap volt per meter. What is the magnetic field at this point? See, magnetic field, use the relationship that the magnetic field, electric field by the magnetic field will be the speed of light. So magnetic field will be electric field by the speed of light. That is 6.3 by 3 into 10 to the power 8, which will be 2.1 into 10 to the power minus 8. But see, this is x-axis, this is j cap. Which axis, Safrina? Electric fields axis.
Why?
Y-axis, j cap is given, no? Ali, axis of magnetic field. Yes, Ali? Axis, z-axis, correct. Magnetic field will be z-axis. So this will be, you can write this as k cap Tesla. Okay. Now another question we will discuss from your board exam. Here frequency and no rule, by the way, but just in case if any question requires the solving part of frequency, remember mega is 10 to the power 6. So you can use this if required. Okay. Write it. One more question we'll practice. Okay, see, let's discuss this question now. What you do whenever the equation is given, you rewrite the equation. 2 into 10 to the power minus 7 sine 0.5 into 10 to the power 3x plus 1.5. Please stop writing, everyone. 10 to the power 11t. This is the value. Now, what you do, you write the actual equation that we have studied. So, the equation that we have studied is b is equal to b naught sine kx plus minus omega t. That's what we've said. Now this question says, see, from here you should be able to identify maximum things. Like magnetic field is this. This is the peak value of magnetic field. Sine. Instead of k, what is coming? This term. So this is your value of k. Instead of omega, you have 1.5 into 10 to the power 11. This is your omega, like this. Now the first part says, class, what is the wavelength and frequency of the wave? See, wavelength is not given directly, but we have the value of k. So we'll use Ck is equal to 2 pi by lambda. So lambda will be 2 pi by k, which is lambda is equal to 2 pi by 0.5 into 10 to the power 3, which is 4 pi into 10 to the power minus 3 meter. This is the wavelength. It says frequency. When nothing is mentioned, by default, the frequency is the linear frequency. Angular will be specified. So it means you'll have to do one or two more steps. That is omega is equal to 2 pi nu. The frequency is equal to omega by 2 pi. So from here, frequency will be equal to omega is 1.5 into 10 to the power 11 by 2 pi. This you can solve later and find out the answer. Okay, 7.25 you can write. Now, this will be hertz. Unit will be hertz, and you can write second. Just calculate it later. Then says write an expression for electric field. See, this part will be the same. When I wrote these two equations here, the above two equations, those were exactly the same. What is different? Instead of B, E will come. Instead of the peak value of magnetic field, peak value of electric field will come. So what you do here for the B part, first calculate E naught. That will be C times B naught. 3 into 10 to the power 8. What's the peak value of magnetic field? 2 into 10 to the power minus 7, which is equal to 60 volt per meter. Now you have the peak value, that's it. Rest of it is not different because it's actually part of the same wave, no? The magnitude of electric field was different and the axis was different. Magnetic field's magnitude is different, axis is different. But ultimately both are of what? They are the part of the same wave. So when I write the expression of electric field, first of all the axis. Now Halima, you will tell me. Look at the question. What do you think the direction of electric field should be there along which axis, Halima? See where the magnetic field is, where the direction of propagation is. Which one is left? Okay, where is the magnetic field, Halima? Halima, you there? Halima Afshin? Yes, Halima, are you attending the class today? You there? No response, Halima. You have not even messaged or anything. Are you there? Ali, can you answer? Where should be the electric field directed? Look at the magnetic fields axis, look at the direction of propagation's axis, and then tell me along with which axis is now left. Ali, can you try? Safrina, what about you?
Negative.
Tell me, where is the magnetic field? Which axis? Look
Y.
at the equation. Which axis?
Y axis.
Okay, Rima, you rejoin. Y-axis. See, so why are you hesitant, Safrina? This is Y written, no? It is Y-axis. That's right. Where is the direction of propagation? Which axis?
X.
X. Which is left now?
Z.
Z. So Z. Okay. This is how you will check. Check these two will be given. Third you have to figure. So yes, EZ will be equal to 60 for the peak value. Sine K is 0.5 into 10 to the power 3x. Now this is the part of the same wave. You don't have to change anything over here. 1.5 into 10 to the power 11t. This much of volt per meter or Newton per coulomb. Anything you can do. Clear? Ali, is it clear to you?
Yes, ma'am.
Okay, please write it. Halima, done? I think you wanted to see this part, no? Done?
Yes.
Halima, Ali, okay.
Yes, ma'am.
Halima, could you write the portion which you asked me to scroll up? You didn't reply anything.
Sorry, ma'am.
You asked me to scroll this up and I scrolled it. Could you write it? Because I couldn't get any response from you.
Yeah, ma'am, I wrote.
You have written? Okay. I think your network is not doing very well today, Halima.
Yes, ma'am.
See, there's a concept of Maxwell's displacement current. Now, I'll start this in the next class only. There's no point of discussing it right now. But I'll just give you a brief what is there in this. Only this topic is left and spectrum. So next class will be our last class for the EMF chapter. That will be on Tuesday. See, Maxwell's displacement current, for this you need to study the Ampere circuital law properly. A little bit about the concepts of the capacitors will be. Basically, the Ampere circuital law got contradicted at a point. What is that point that I'll tell you later? But Ampere circuital law got contradicted at a point. So Maxwell said that only the current that we are able to see and the current that we are able to use till now, that is not the sole current that is working. Because if it was, then at every case you should get the Ampere circuital law perfect. But that's not the thing. So if you are not getting the Ampere circuital law perfect, it means there is some more current, some other current also which is present, which we are neglecting. So that current was the displacement current, and Why does it come and how does it come? All these things I'll tell in the next class. So till here, have you understood EM-based chapter, the first portion of it? All of you. Next week, we'll just complete this off so that we aren't left with anything. Okay. All right then.
Okay, ma'am.
Okay then. Thank you. All right. Please do the assignments class. In the next class, I'll have to discuss some AC. Why are you not submitting the assignments? From alternating current, only few students have given very few assignments. That's why I didn't discuss any of the assignments of AC till EMI chapter we have